In this lesson, we're going to learn change of state. So, this is about change of state of matter. So, from liquid to solid, and properties of liquids we're going to learn, and liquid to vapor. So, properties of gases. So matter can change its states, no? So what is liquid to solid changes. So they said, according to your Egans, no, all matters can change state because respiratory therapies work extensively with the both liquid and gases. So they must have a good understanding of the key characteristics of these states and the basic processes underlying their phase changes. So why it is very fundamental to learn the changes when it comes to the state of matter, because we work in the hospital extensively with both liquids. When we say liquids, we work with the body fluids, the different blood uh, test, or like arterial blood gas and gases. For example, we put oxygen, full concentrated of oxygen into the lungs using a mechanical ventilator. So we need to understand these changes. So liquid solid phase. So the change, melting and freezing. So in this topic, we learn that kinetic energy, when a solid is heated, its molecular kinetic energy increases. This added internal energy increases molecular vibration. If enough heat is applied, these vibrations eventually weaken the intermolecular attractive forces. So, at some point, molecules break free of their rigid structure and the solid changes into liquid. So, because of the friction, no? So, because of this kinetic energy, they changes to another phase into a liquid. So, that is one definition of for kinetic energy. So, melting. So, melting is the change over from solid to liquid state. That is called melting. So that is very basic, no? So this is the example of in the figure where you can see the melting phase. So freezing is the opposite of melting. So why? Because melting requires large amounts of extremely applied energy. Who would expect you would expect what you call freezing to return this energy to the surrounding, and this is exactly what occurs. So during freezing, heat energy is transferred from a liquid back to the environment, so usually by exposure to cold. So as kinetic energy as kinetic energy of certain substance decrease, no, let's move the cam. So decrease its molecules begin to regain the stable structures of a solid. According to the first law of thermodynamics, so let's review the first law of thermodynamics. The energy required to freeze a substance must equal the needed to melt it. So the freezing and melting points of the substance are the same. So they maintain the same equilibrium, no? Or in the balanced states. Sublimation. So sublimation is the term used for the phase uh, transition from a solid to a vapor without becoming a liquid as an intermediary form. An example of sublimation is dry ice, so frozen carbon dioxide. So dry ice sublimates from its solid from into a gaseous carbon dioxide with first melting and becoming liquid carbon dioxide. So that is sublimation. So properties of liquids. What are the properties of liquids? So liquids exhibits flow and assume the shape of their containers. So they adapt to a certain shapes, no? Liquids also exert pressure which varies with depth and density. So several variation in liquid pressure within a container produce an upward support force called buoyancy. So it is an upward force we called again buoyancy. So pressure in liquids. Liquids exert pressure which has the dimensions of force per unit area. Force per unit area again. The pressure exerted by a liquid depends on both its height, depth, and weight, density or weight per unit volume, which is shown in the equation form. So this example of pressure in liquids is equal height times the depth and weight or and of an object, where P or pressure in liquids or PL is the static pressure exerted by the liquid. So and the H in the equation is the height of the liquid column and the dW is the liquid's weight density. For example, to compute the pressure of at the bottom of 33.9 feet, it's converted into centimeters height column of water and density of 1 gram per cubic centimeters. You would use the equation that the pressure of liquid is equals to height times the density. So that is the formula of our pressure in liquid. So you do the substitution of the equation. So you go back to your EGANs and you can see the formula. So this is the Pascal's principle. So they adapt to a certain shape. No, so physical principles of respiratory care. This is can be seen in your EGANs. No, so this is the Pascal principles. So we need also to review the Archimedes principle. So Archimedes principle, thousands of years ago, Archimedes showed an object submerged in water appeared to weight less than in air. This effect called buoyancy. So this is what we call buoyancy. Explains why certain objects float in water. Liquids exert buoyant force because the pressure below a submerged object always exceed the pressure above. So there will be an opposite pressure, no? So that's what we call buoyancy. This difference in liquid pressure creates an upward buoyancy force most equal to the weight of the fluids, no? So let's move the cam again. Fluids displaced by the object, and the buoyancy force may be calculated as follows. So that's the equation for buoyancy. So when we say buoyancy, it reflects the Archimedes principles. So viscosity, we define viscosity as the force opposing a fluid's flow and is similar to friction in solids. So the viscosity of fluid is directly proportional to the cohesive force. Again, it's directly proportional to the cohesive force or forces between its molecules. The stronger these cohesive forces are, the greater the fluid's viscosity. So remember that uh, definition. So deeper uh, overview about viscosity. So the underlying to understand the understanding of viscosity leads to the concept that fluids move in discrete cylindrical layers called streamlines. So this pattern of motion is called laminar flow. So laminar flow is viewed as concentric layers of fluid flowing parallel to the tube wall or velocities that increase towards the center. As shown in the figure 6.6 of your EGANS, no, frictional forces between the streamlines and the tube wall impedes movement of the outer layers of the fluid. Each layer moving towards the center of the tube hinders the motion of the next inner layer less and less. So the difference in the viscous velocity among these concentric layers is called the shear rate. So shear rate and is simply measured of how easily these layers separate. Shear rate depends on two factors. One, the pressure pushing or driving the fluid called a shear stress. Again, so the pressure pushing or driving the fluid is called shear stress. Second, the viscosity of the fluid. Second is the viscosity of the fluid. Shear rate is directly proportional to shear stress and inversely proportional to viscosity. In uniform fluids such as water or oil, viscosity varies with temperature because higher temperatures weaken the cohesive force between molecules. Heating and uniform fluid reduce its viscosity. Conversely, cooling on a cold winter morning, the oil or our oil in our automobile becomes so viscous that impedes the movement of the engine parts. So you need to warm up first, or you experience hard start when during winter on your automobile, no? So when you're starting your car during winter or cold weather, there are such a problem when we say to our car engine because this impedes the movement of engine part due to our viscosity. So nawala si slide natin. Wait. Understanding viscosity. So this is all about viscosity, no? So ang hirap ng slide. So the blood. So what is all in the blood? Blood is a contrast to water, or let's it's comparable. So blood is, in contrast to water or oil, is a complex fluid that contains not only liquid plasma, which is 90% water, but also cells is but also cells in suspension. For this reason, blood has a viscosity approximately 5 times greater than the viscosity of water. So blood is more viscous compared to your water. So the greater the viscosity of the fluid, the more energy is needed to make it flow. So the heart works harder to pump blood than it would it if the pumping water because of this viscosity. So the heart must perform even more work when blood viscosity increases. So as occurs in uh, polycythemia or increase in red blood cells concentration in the blood. So that is one example of viscosity abnormality in your body, the polycythemia. So nawala siya pag kiniklik. Hirap ng So cohesion and adhesion. So this is all about cohesion and so what is cohesion and adhesion? So the attractive force between the same molecules is called cohesion. So the attractive force between unlike molecules is called adhesion. So these forces can be observed at work by placing a liquid into a small diameter tube. As shown in the figure 6.7, the top of the liquid forms a curved surface. So this is what we call the meniscus. So why we need to study meniscus? So in flow meter, the ball, no, if you adjust the ball, if your flow meter using oxygen therapy, so the 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 accurate lining of your FiO2 in the flow meter is on the bottom of the ball. Hindi mo pwede ilagay yung bola sa 2 liters per minute on the center because we are observing the lower meniscus, no? So sa flow meter is not targeted on the center. May bola kasi yan. So in a flow meter of an oxygen, so you need to uh, calibrate or align the level. Example, when you are using 2 liters of oxygen to LPM, you need to place your measurement to the lower ball or what we call the lower meniscus. So when the liquid is water, the meniscus is concave because of water molecules. So in the volume what we call graduated cylinder. So you observe when you put water, so concave, hindi siya flat yung water level in your what we call graduated cylinder, no, sa chemistry nyo, because of the reason water molecules at the surface adheres to the glass more strongly than they coheres to each other. So concave ang sa graduated cylinder, that is what we call the meniscus level, no? In contrast, a mercury meniscus is convex. So in this case, the cohesive forces pulling the mercury atoms together exceed the adhesive forces trying to attract the mercury to the glass. So you observe that the water in your graduated cylinder is concave, no? So that is all about the meniscus. So in this figure, so you observe this is the meniscus, concave ang liquid o volume of liquid sa isang graduated cylinder or a test tube. Surface tension. So surface tension is force per unit length equivalent to surface energy density with units of Newton meter. exerted by like molecules at the surface of liquid. A small drop of fluid provides a good illustration of this force. So this is the structure of your surface tension. So spring type, no hexal. So sometimes, yeah, it's like an intertwined structure. Surface tension is quantified by measurement of the force needed to produce a tear in a fluid surface layer. In table 6.2 lists the surface tensions of selected liquids in dynes per centimeters. For a given liquid, surface tension varies inversely with temperature. So the higher the temperature, the lower is surface tension. So indirectly or in opposite sila, no? The higher the temperature, always remember, the lower its surface tension. So surface tension plays an important role in determining the relative size of connected alveoli. What is alveoli? That is the grape-like structure of the lungs, the alveolar capillary membrane, wherein the gas diffusion occur. So you may relate the surface tension. So again, surface tension plays an important role in determining the relative sizes of concentrated or connected alveoli. So to understand this, consider spherical bubbles of air in a liquid, what we call analogs to alveolus, no? According to the Laplace law, what is Laplace law? You need to understand Laplace law. So Laplace law is the pressure inside the bubble varies directly with the surface tension of the liquid and inversely with its radius. So that is the definition of Laplace law. The pressure inside the bubble varies directly with the surface tension of the liquid and inversely with the radius. So internal surface tension will attempt to contract the bubbles but it is opposed or contradicted by the resulting pressure inside the bubbles. So to increase the radius by an amount of diameter, we must perform work where d represent the infinitesimal changes used in calculus. So it is related to calculus, no? That is the principle of law of Laplace. So capillary action. What is capillary action? So it is a phenomenon in which a liquid in small tube moves upward against gravity. So capillary action involves both adhesive and surface tension force. So as shown in the figure as 610a, the adhesion of water molecules to the walls of a thin tube causes the upward force on the edge of the liquid to produces a concave meniscus. So that is capillary action. So parang nagkaroon siya ng concave shape. Ito yon. So this the net upward force, the meniscus. So this is the lower meniscus of your in this figure. So the force of your addition can be appreciated in this illustration of the concave figure of the liquid. So concave or convex is the same. So liquid vapor phase changes. So boiling. So the boiling point of the liquid is the temperature at which the vapor pressure exceed the atmospheric pressure. So when liquid boils, the molecules must have enough kinetic energy to force themselves into the atmosphere. Then again, against the opposing pressure, because the weight of the atmosphere retards the what we call the escape of the vapor molecules. So that is a definition of boiling. So evaporation, vapor, pressure, and humidity. So boiling is only one type of vaporization. So you convert a liquid into a vapor form. So a liquid also can change into a gases at temperature lower than the boiling point, enough a process called evaporation. So water is a good example. When at temperature lower than its boiling point, water enters the atmosphere via evaporation. So evaporation so requires heat. So the heat energy requires for evaporation comes from the air next to the water surface. As the surrounding air loses heat energy, so it cools. So this is the principles of evaporative cooling effect, which is previously described. So if the container is covered, water vapor molecules continue to enter air until it can hold no more water. So at this point, the air is over the water is saturated with water vapor. However, vaporization does not stop when saturation occurs. Instead, for every molecule escaping into the air, another returns to the water reservoir. These conditions are referred as the state of equilibrium. So that is for your evaporation. So influence of temperature. So why temperature influence such matter? So influence of temperature. No other factor influences evaporation more than temperature. So temperature affects evaporation in two ways. First, the warmer the air, the more vapor it can hold. Specifically, the capacity of air to hold water vapor increases with temperature. The warmer the air contracting the water surface, the faster the rate of evaporation. So that's why in connection with human anatomy, no? So the main function of your nares, of your nose, is olfaction, filtration, humidification. So let's review the normal physiology of your nose. So that's why it is vital that as a respiratory therapist, we understand the normal physiology. So simply, the function of your nose. So if you dissect it, it has a nasal conchae, no? May mga nasal conchae ang nose to create a turbulence effect on the gas flow. So as the gas flow enters your nostril, it will go to the normal anatomic structure, the nasal conchae, which is more on cylindrical, we will say concave shape, that the air contact to the body will create a turbulence. So this turbulence will create a warmer temperature of the air before contacting to your lungs. So the structure of your upper airway is designed for a warmer air contact so that the air going to your lungs will be humidified. So there is a process of normal humidification based on your normal physiology. So that is how God is bright and created the normal physiology of human. So there is a normal humidifier. In such, during intubation, so when we put patient in an artificial airway, we bypass the upper airway. So there is an absence of normal humidification due to due to these artificial tubes, what we call the endotracheal tube, the tracheostomy tube. So there is a bypass again of normal humidification. So as a respiratory therapist, we need to maintain proper humidification. So we use condensers, humidifiers, heat and moisture exchangers during hooking a patient in our mechanical ventilator. So we will fully understand this what we call humidification process when you take up mechanical ventilation as your major subject in your respiratory uh, study. So this is only an overview how humidification is important in respiratory care. So we used to need to substitute or need to maintain this artificially during clinical scenarios. So since we use artificial airway, bypass yung nose mo. So the patient cannot humidify the air coming to his lungs. So that is the science of respiratory therapy. So how can you maintain a normal body temperature or your normal humidification of gases going to the lungs? So this will be taken up to your mechanical ventilator subject, no? So the importance of humidity therapy. So speaking of humidity, so we define humidity, water vapor pressure represent the kinetic activity of water molecules in air. So there should be a kinetic movement of water vapor on your tubings, no? So that is the humidity. Uh, for actual amount of weight of water vapor in gas to be determined, the water vapor content or absolute humidity must be measured. So there are two types of humidity. As we go further for this discipline, so we have the relative humidity or the RH and the absolute humidity or the AH. No, so that's all about humidity. We have absolute humidity and relative humidity. So when gas is not fully saturated, its water vapor content can be expressed in relative terms using measure called relative humidity or RH. So the RH of gas or the relative humidity of gas is the ratio of its actual water vapor content to its saturation capacity at a given temperature, whereas the relative humidity is expressed as the percentage as derived with the following simple formula. So the content of relative humidity in percentage is equal to the capacity times 100%. That's the equation. So for example, saturated air. So saturated air at the room temperature of 20 degrees centigrade has the capacity to hold 17.3 milligrams per liter of water vapor. So in your figure table 6.3, no, so you see and review the table 6.3. So if the absolute humidity of 12 milligrams per liter, the relative humidity is calculated as follows. So review the equation. So relative humidity is equal to 12 milligrams per liter. So that's 17.3 milligrams per liter times 100% of your relative humidity. The answer will be 0.69 times 100% relative humidity. So the relative humidity will be 69%. No. So let's you review the book of in this chapter about relative humidity. This is just an overview. So a decrease in capacity would have the opposite effect in figure 6.13. We start a large glasses which have full of 50% relative humidity. So the capacity of the glass to decrease the pouring of the water into the progressive smaller glasses. So that's the what example of the illustration. No? So equivalent to the decreasing of the gas temperature. Eventually, the water volume is enough to fill a smaller glass, which is 100% relative humidity. So what happens if we try to empty these full glasses into an even smaller one? So what will be the expected result? Because the smaller the glass has less capacity. So the excess content must spill over. So the will spill off, no? So this spillover is analogous to the condensation occurring when saturated gas cools below its dew point. So there will be an overspill. So that's the one illustration of how this principle is explained, no? The relative humidity. So you compare, contrast, and correlate on the figure of your book. However, although condensation has removed the excess moisture from the air, the smaller glasses is still full 100% of relative humidity. So it's an illustrative explanation about relative humidity. Pag kiniklik ko sa slides, nawawala siya. So next slides. So in clinical practice, relative humidity again, two additional measure of humidity are choose percent body humidity or the body percent pH, we call it in acronym BH, the percent body humidity, and humidity deficit. Or so remember, in clinical practice we have the percent body humidity and the humidity deficit. So the percent body humidity of a gas is ratio of its actual water vapor content to the water vapor capacity in saturated gas at the body temperature of 37 degrees centigrade. So the percent body humidity is the same as the relative humidity, except that the capacity or the denominator is fixed at 43.8 milligrams per liter. So guided by this equation, I think there is an equation for this. There is a fixed denominator of 43.8 milligrams per liters. So how pressure influence, so the influence of pressure. So high temperatures increases vaporization, whereas high pressure impede this process. So water molecules trying to escape from liquid surface must push their way out against the opposing air molecules. If the surrounding air pressure is high, there are more opposing air, no? So air molecules and vaporization so decreases. Alternatively, low atmospheric pressure increases vaporization. Again, if there will be low atmospheric pressures, so it increases the vaporization. So last topic of this slide, influence of surface area. So influencing the surface area. When we say surface area, what is the meaning? So the greater the availability of surface area of the gas in contact with air, the greater the rate of liquid evaporation. So what is the influence of surface area in respiratory care? So it's the PEEP, or the positive and expiratory pressure. So it creates a greater surface area of your alveoli, no? So when we put patient in a ventilator, we are implementing the PEEP. So we have an intrinsic PEEP or normal PEEP of 3 to 5 centimeters of water. So that's the normal physiology. So when we put patient in the ventilator, so sometimes patient experience atelectasis where their alveoli collapse. So let's review the basic principles of the surface area. So anong sabi sa textbook? The greater the availability of surface area of the gas in contact with the air, the greater the rate of liquid evaporation. So this statement or this definition can be easily proved by comparing how quickly equal volume of water evaporates under dry condition from a flat plate versus from atoll, so narrow glasses. So the water spread over a flat plate evaporates more quickly to compare with the same amount of liquid in atoll narrow glasses. So pag malaki ang surface area mo, mas greater ang evaporation, where in closed or tall narrow glass, mas less ang evaporation. This principle is applied again This principle is applied to the design of the certain humidifiers to increase their ability to put water vapor in the passing gas, or what we call active humidifiers in ventilators. So your nose as bypass, because nag-intubate ka ng pasyente, you put artificial airway in your patient. So saan dumadaan yung endotracheal tube? Syempre in your mouth, no? So remember that the lower the surface area of certain humidifier. So that's why hindi mo pwedeng gamitin yung pediatric humidifier compare sa adult humidifier mo, kasi the dead space or the container of your humidifier of your ventilator is different from pedia to an adult humidifier. So you need to consider the surface area in relation with your evaporation process. So the larger the surface area, the greater is the evaporation. So that is simple, no? So we can say use the alpha, or what we call directly proportional, ang concept ng sinasabing evaporation in terms of surface area. So I think this is the last slide for this topic. So for the next lesson, be ready for your canvas. We will be posting another topic on thermodynamics. Okay, thank you for your time, and prepare and review under the canvas quizzes for some learning kits regarding or related in this topic to enhance your uh, skills regarding the states of matter. Thank you. 1, 2, 3.